Hi, welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers of the Space Telescope Science Institute. It's early May 2009, and this is a picture of the Space Shuttle Atlantis on Launch Pad 39A at Kennedy Space Center in Florida. It is preparing for a scheduled May 11th launch for a mission to service the Hubble Space Telescope. And during this Space Shuttle mission, the astronauts will bring Hubble into the cargo bay. They're going to add 2 new science instruments. They're going to try and repair 2 current science instruments on Hubble that have had electrical failures. They're going to replace a lot of equipment, and they're going to basically have one of the most ambitious servicing missions we've ever attempted. It's really going to be quite an exciting event. Now, the media coverage of Servicing Mission 4 often focuses on the astronauts, and they deserve it. They're amazing people doing some amazing stuff. Or you also hear a lot about the hardware, the instruments that are going in, the repairs that they're making to the Hubble Space Telescope. But what you don't hear often enough, at least in my opinion, is the science behind it. Why are we really doing this? We're doing this to make Hubble a better observing instrument for astronomers. And we're really doing it so that we enable more science to be done. And that's what I'd like to talk about in this episode, the science that will be enabled by Servicing Mission 4. And really, I want to talk about the new instruments that we're putting on Hubble and the science that that will enable. The first one I'd like to talk about is this, the Wide Field Camera 3, or as we shorten it around here to WFC 3. And as you can see from this image, it's about the size of a piano. And it's going to go into Hubble, and it's going to replace the Wide Field Planetary Camera 2. As a matter of fact, it's the same size and shape as Wide Field Planetary Camera 2. And really, we're just going to pull out WFPIC 2 and put in WFC 3. And so WFC 3 is going to be a much better instrument because it's upgraded technology. Sort of like in your computer. When you pull out an old video card and pop in a new video card, you get brand new capabilities. Well, that's the same thing we're going to do with Hubble. And here is a graph to sort of show you how much better WFC 3 is over the previous instruments on Hubble. So on this graph, we have sort of what's called throughput times area on the x-axis, which is basically the amount of data that Hubble can observe per second. And on the y-axis is wavelength, okay? And this region over here is the ultraviolet region. This region in the center is the visible light region. And over here on the left, we have the infrared region of the spectrum. Now, this blue curve here is the sort of the sensitivity of Wide Field Camera 3, and this green curve down here is the sensitivity of Wide Field Planetary Camera 2. And in this graph, higher is better. You'll also note that this graph is logarithmic, so this is about a factor of 10. So over here in the ultraviolet, it's going to be more than 10 times better than what we could achieve with PIC 2. And in the visible light, it's a few times better. And over here in the infrared, well, it's going to be more than 10 times better. So Wide Field Camera 3 is not only going to cover the entire range of wavelengths that Hubble can observe from ultraviolet to the infrared, but it's also going to do so 3 to 10 or even more times better than previous instruments on Hubble. This makes WFC 3 the first truly panchromatic camera that we've had up there. We can cover from ultraviolet to the infrared in one instrument. And that's really powerful. What sort of power does that give us? Well, let me illustrate with this image of a galaxy. Now, this is not just an image of a galaxy like you take with your Instamatic camera, click, all right, and this is what it looks like. This image is actually a composite of many different filters from many different wavelengths. So, this animation is going to show you some of those wavelengths. Here, for example, is the ultraviolet image shown in blue, and in that we see the young stars, the really newborn stars. Here shown in green are sort of the normal stars, the older stars, the everyday stars. In yellow, we're showing you the nebula, the regions in the galaxy where stars are born. In orange, we're sort of showing you the middle-aged stars, a little bit older stars that show up in longer wavelengths. And here in the red, we're showing you the oldest stars. And this image here was actually taken in the infrared. So, by having many different filters across many different wavelengths, we get several views of this galaxy. And when you combine them together, you get a much richer view of the galaxy than you otherwise would just taking one single wavelength. So In this animation, we've shown you 1, 2, 3, 4, 5 different filters, 5 different wavelength observations of the same object, and we see different things in it. But WIFC-3 doesn't have just 5 filters. In fact, across its 2 cameras, it has about 61 different filters. So we can observe galaxies or stars or nebulae or other astronomical objects in 61 different ways and extract as much information as possible. That's the value of having a truly panchromatic camera up there on Hubble. Now, I told you when I showed you that graph that it's especially good in the infrared and in the ultraviolet. And let me tell you a couple things, a couple science points that the infrared and the ultraviolet will enable us to look at. In the infrared, we'll be able to look at things like this, planetary disks around new-forming stars. Okay, now this is an artist's visualization. This is not what Hubble will see, unfortunately. At least not for many years will astronomers be able to get images like this. But this is a newborn star here in the center, and around it there's this big dark dust disk. Inside this disk, planets are expected to be forming. Now you'll notice I said dark dust disk, okay? That's because in visible light, it's dark. It doesn't radiate invisible light. So we can't see it in visible light. However, the dust in this disk is heated by the star in the center, so it has a certain temperature and therefore radiates in the infrared. It's warm enough to glow in infrared wavelengths. So the enhanced capability of WIFC-3 in infrared will allow us to study these disks around newborn stars much better than we previously had been able to. We'll also, with infrared capabilities, be able to study galaxies, and not just nearby galaxies, but really, really distant galaxies. This image is the Hubble Ultra Deep Field, and it's basically a collection of about 10,000 galaxies all the way across the universe. Okay, we've got nearby galaxies, we've got really distant galaxies. And one of the most distant galaxies is located right here. You can't see it. Actually, it's much too small to see in this scale, so let me blow it up. Can you see it now? Can you pick out which one it is? You probably can't, but let me just point it out to you that it's this little red dot here, okay? This little red dot is a galaxy, or actually probably a galaxy that's just beginning to form, that is over 12 billion light years away. The light from this galaxy has been traveling for 12 billion years across space before Hubble observed it. And the reason that it's red is related to its distance. Because as the light travels for 12 billion years across space, space is expanding. Remember, we live in an expanding universe. And the light of that galaxy gets stretched along with the expansion of space. So the light from this galaxy may have started out in the ultraviolet or the visible, but by the time we see it, it's stretched to longer wavelengths, and we observe it in the infrared. So infrared capabilities of WIFC-3 will allow it to study the most distant objects in the universe. We'll see many more of these red dots, and hopefully we'll see them in a little bit more detail than just being dots. Now, that's the infrared capabilities of WIFC-3. The ultraviolet capabilities, well, they're well illustrated by this image. This is an image of the antennae galaxies. The antennae galaxies are 2 galaxies that have come smashing together. And these are the cores of the 2 galaxies. And you can see all this incredible burst of star formation. Because when galaxies collide, the gas clouds then collapse, and you get huge amounts of star formation, tons and tons of star formation. And you get bright, young stars that emit very heavily in the ultraviolet. And WIFC-3, this wasn't taken with WIFC-3, but when we see images from WIFC-3 of images like this, we will really be able to study these star formation regions in exquisite detail. The second instrument that's going to be installed during servicing mission 4 is the Cosmic Origin Spectrograph, and that is also optimized for ultraviolet radiation. This is a picture of the Cosmic Origin Spectrograph, and you can see, well, it's about the size of a telephone booth. Actually, all of the radial instruments on Hubble are pretty much look just like this. They're big boxes about the size of a telephone booth. Now, let me explain, first of all, what a spectrograph is. Okay? People are used to cameras and imaging, but they're not quite so used to the idea of spectra. But it's not that hard. First of all, if you take the light, white light, and use a prism to spread it out, you get a rainbow. We call this simply a spectrum. Okay? So this is the spectrum of visible light. Not too much science we're going to learn, at least in today, from just looking at a rainbow, right? But where it becomes interesting is when you start to look at individual elements. This is the spectrum that one gets from looking at the element hydrogen. The middle one is the spectrum of the element helium. And the bottom one is the spectrum of the element neon. What's going on here is that each atom has electrons orbiting the nucleus, right? And those electrons have distinct orbital levels. And they can jump around between those orbital levels, each orbital level having a specific energy. So when it jumps from the third level down to the second level, it always changes energy by the same amount and therefore emits a wavelength of radiation of the same wavelength. Right? It emits radiation always of that same energy. So what you are seeing here in these specific spectral lines, that's what we call them, spectral lines, is electrons jumping around inside atoms, and every transition has a specific line associated with it. And so you can see hydrogen, which only has one electron, has a relatively simple spectrum, while helium has two electrons, and it has a little bit more complex structure, and neon has many more and even more complex structure. The point is that the spectrum of each element is unique. Now, let's combine the two ideas. If, for example, we have a complete rainbow of color, let's say from a star, but in the atmosphere of that star, we have certain elements. Now, those elements will be cooler than the star that's emitting it, so instead of creating radiation, they'll be absorbing the radiation at those specific levels, and so therefore they'll appear as black spectral lines in the overall spectrum. Right? This is basically a low-resolution spectrum of a drawing, actually, of a low-resolution spectrum of what our sun might look like. If you want to know what a scientist would look at, well, instead of being about a yard long here, let's stretch this out to be a football field long, or perhaps 2 football field longs, so you get really detailed look at the wavelengths. And then in order to show it in one image, what we're going to do is we're going to chop that spectrum up into pieces so that, you know, the start of this here is the end of this over here. So these are all just pieces of one really, really, really long spectrum. And this is what you would see for the spectrum of our sun. Okay? Covering the whole visible light wavelength region, but look at all the various spectral lines. These indicate all the elements that are present in the sun's atmosphere. And one of the cool things is that we actually discovered the element helium in the spectrum of the sun before we found helium here on Earth. So we really can, once you learn the code, once you figure out how to decode all of this information here, you can actually figure out the elements that are out in the universe just by looking at the spectrum. And so that's what a spectrograph does. It takes the light of a star or a galaxy or any other astronomical object, spreads it out really, really far, and takes a look at the intensity versus wavelength. And that tells you information about the elements, their temperature, their motion, and you can figure out what's happening way out there in the universe by looking at the spectrum. Now, I know that was a long digression, but it's really important for understanding why the cosmic origin spectrograph will give us really great results. Now, first of all, it's going to be better than the previous instruments on Hubble. Of course, we wouldn't put them up there. This is a graph, well, in the strange sense of science, in this graph, actually, the lower is better on this graph, okay? And this is wavelength here on the y-axis again, but this is all in the ultraviolet region. And so here, this blue line here and this purple line here represent the sensitivity of the cosmic origin spectrograph, or COS. And this green and red line refer to the sensitivity of the Space Telescope imaging spectrograph, current spectrograph on Hubble. And you can see that since lower is better, and again, this is logarithmic, it's going to be about a factor of 3 to maybe about a factor of 10 times more sensitive than the Space Telescope imaging spectrograph. Now, what science are we going to do with it? What are we going to look at? Well, it's called the Cosmic Origin Spectrograph because one of its major goals is to study large-scale structure in the universe. Large-scale structure, what's that? Well, we have an animation to help explain that. This is an artist's idea of our Milky Way galaxy, along with the large and small Magellanic Clouds, our companion galaxies. And in this animation, we're going to slowly back away from our galaxy, and in come the galaxies of our local group, which is about a few dozen galaxies nearby us. And as we move further and further away, we start to see galaxies in other groups of galaxies nearby. And so you can see that galaxies are collected into groups, and they're even collected into large clusters like this one. This is the giant Virgo cluster, a collection of thousands of galaxies. But on still larger scales, on the large-scale structure of the universe, all of the dots in this part of the animation would be entire clusters of galaxies. And those clusters are connected by these long stringy things we call filaments. And then there are these big empty regions that we call voids. And the structures between these clusters give us the large-scale structure of the universe. But this is sort of misleading here, because this is a computer simulation. This is a simulation of large-scale structure that has then been visualized. And unfortunately, Hubble doesn't get cool pictures like this to see the large-scale structure of the universe. Most of what we see here isn't visible by Hubble. So how do we then determine the ideas of the large-scale structure of the universe? Well, we do it using COS. All right? Now, in this diagram, we have the large-scale structure of the universe schematically represented by a computer simulation, and Hubble over here. And Hubble is looking at a very distant, very bright object. It would probably be a QSO, which stands for quasi-stellar object. And we believe these QSOs are supermassive black holes at the centers of galaxies that are emitting a huge amount of radiation, okay? So much so that we can see them half to two-thirds of the way across the universe. And so you've got the bright light from this QSO, represented by the full spectrum here. But as that light passes through large-scale structures in the universe, other clouds and clumps of matter in the universe, well, then the elements in that matter will absorb some of the light, and its elements will leave fingerprints on the spectrum. And as it passes through another one, there'll be more stuff, and then another, there'll be more lines added to it. So like looking at the spectrum of the sun, where you had to learn to deduce what the elements are there based upon the pattern of spectral lines, here the pattern of spectral lines will show us the matter that's in between us and the QSO. And so as we learn to understand what the lines are, we can deduce the structure of the universe. And it's important to be able to do this in the ultraviolet, because one of the main absorption lines of hydrogen, and hydrogen is the dominant element in the universe, happens to occur in the ultraviolet. So COS will be able to look in the ultraviolet, look at very distant objects, and see the evidence of the matter in between in the spectra that it records. So those are the two new science instruments that will be put into Hubble in Servicing Mission 4. And perhaps by the time you watch this, Servicing Mission 4 has already completed, and I hope it was a fantastic success. If it was a great success and things go on schedule, we'll be able to see the latest results from WIFC-3 and from COS in the fall of 2009. Well, that's it for this episode of Hubble's Universe Unfiltered. If you want to comment on it, or you have some questions that I didn't answer, you can now contact us on Twitter. We're at twitter.com/Hubble's Universe. Send us your comments, your questions, anything you'd like to see on Hubble's Universe Unfiltered, and we'll try to respond to as many of them as we can. We'll see you next time. Take care.